In this video, we are going to look at some carefully selected questions in general organic chemistry. Name the following compounds indicating stereochemistry where possible. Now, if we consider this compound, let's determine the parent chain. So this is 1, 2, 3, 4, 5, 6, 7. So 7 carbons. So we know that we have a hept. Now there are 2 alkenes inside, so it is a heptadiene. So this is a heptadiene. However, the alkenes, the double bonds are on carbon number 2 and carbon number 4. So it is a 2,4 heptadiene. Then we have substituents on carbon number 1 and then on carbon number 5. So we have a 2,5 dimethyl 2,4 heptadiene. Sorry, so there's something I omitted here. There is a methyl here. So the next thing is to determine the stereochemistry of this molecule. Now you see that here there is no stereochemistry because this methyl is equal to this one, but there is stereochemistry here. So if we divide this double bond into 2, if we come here, you see that here is 1 and this is 2. We'll give precedence to this one over this. And if we come to this side of the double bond, this is an ethyl, so this is 1 and then the methyl is 2. So you see that the substituents of higher priority are on opposite side of the double bond. So this is an E, so we actually have a 4E. So this is 4E. Then we have a substituent, methyl substituent on carbon number 2, then also on number 4 and then number 5. So 2,4,5 trimethyl, then 2,4 heptadiene. So that is the name of that molecule. Now let's come to this molecule. Now if you look at this molecule, let's determine the parent chain. So the parent chain is, if we start from here, this 1, 2, 3, 4, 5, 6, 7. And if we start from here too, it is 1, 2, 3, 4, 5, 6, 7. So anyway we start, we still get this methyl on the list number. So if we start from here, this is 1, 2, 3, 4, 5, then 6, and then 7. So we also have 7 carbons in this molecule, and then there are 2 alkene groups. So this is also a heptadiene, but this is a 2,5 heptadiene. Now let's determine the stereochemistry on the molecule. But you see there is no stereochemistry. This is not a stereocenter because this arm of the molecule is equal to this side, and therefore this is not a stereocenter. However, there is stereochemistry here. There is a proton here, and then there is also a proton here. So if we are supposed to give priorities, then here will be 1 and this will be 2. If we divide the molecule into the double bond into 2, then here is 1 and this is 2. So you see that the 2's are on the same sides and the 1's are also on the same side of the double bond. So we have a 2Z. Apart from that, there's also a stereochemistry here. This is a proton, this is a proton. So if we divide this molecule into 2, the double bond into 2, then we find out that we give precedence to the methyl group over the proton. So this is 1 and this is 2. And in this case, this is 1 and then this is 2. So the 2's are also on the same side and the 1's are also on the same side. So we also have a 5Z. So at the end of the day, this is a 2Z, 5Z. Then there's a methyl group substituent here, 4-methyl. But the alkenes are on carbon number 2 and 5. So it is 2,5 heptadiene. So those are the names of those molecules. Now let's come here. It says we should assign E or Z. Now the first thing is divide the alkene bond into two. Then now, if we come here, this is a nitrogen. It has a higher molar mass than a carbon. So here's 1, here's 2. If we come here, this is a carbon bonded to a proton that is bonded to an oxygen. But this is a carbon doubly bonded to an oxygen. So this is 1, and then this is 2. So in this case, you can see that the 1s are on one side, and then the 2s are also on another side of the double bond. So this is a cis molecule. So this is a Z. So the configuration of this molecule is Z because it's a cis. Now let's come to this molecule. So this is a cis. So now let's come to this molecule. If we divide the double bond into two, this side and this side is the same, but this side is different from this side. So this side is 1 and this side is 2. Then when we come here, this is 1 and then this is 2. So you see that 1s are on the opposite side of the double bond, and then the 2s are also on the opposite side. So this is a trans molecule. Because a trans molecule is an E. Now let's come to this molecule too. Now if we divide this into 2, if we come here, this is 1, this is 2. And then if we come here, this is a triple bond. We will give precedence to this one over this, and then this is 2. So at the end of the day, this is going to, the 1s are on the opposite side of the double bond, and the 2s are also on the opposite side. So this is also a trans molecule, and therefore this is an E. Draw three-dimensional structures of the following. A. S1 bromo, 1 chloro, 1 iodoethane. And then 2 is 1 bromo, 1 phenyletane. So let's first draw the structure before we draw the three-dimensional structure. So we are talking about iodoethane. So this is our ethane. And then we have 1 iodo. So there's an iodine group here. And then we also have 1 bromo. There's a bromo group here. And then we have 1 chloro. So there's also a chlorine group here. So this is how the molecule is. So now let's try and draw this molecule in three-dimensional structure. However, it's an S, so we need to observe the rule. So, but then let's first give priorities. Now, iodine has a larger atomic number than bromine. So iodine is 1, then bromine is 2, and then chlorine is 3, and then the methyl group is 4. So the least group, which is the methyl group, is number 4, and we know that the least group is supposed to be on the wedge bond. Now let's put bromine and chlorine in the plane of the molecule. So let's do this. So this is bromine, and then this is chlorine. Then now the iodine is the one with the highest priority. Let's put it on a wedge bond. So it is coming out of the page. So this is iodine. And then the methyl, which is the least group, we'll put it on the dash bond. So this is the methyl. Now let's determine the configuration of this molecule. So iodine is 1, and then bromine is 2, and then chlorine is 3, and then the methyl is number 4. So you see that it is going in the anti-clockwise direction, which is an S. So this is the structure of the molecule of S1 bromo, 1 chloro, 1 iodoethane. Now let's come to R1 bromo, 1 phenyletane. Let's just draw the molecule. So we are talking about a phenyl group. So this is how a phenyl group looks like. And then it is connected to an ethane. So this is an ethane. And then 1 bromo. So we have a bromine. That is, and then we know that we have a proton because carbon bond, there's 4 bonds. Now let's assign priority. So bromine is the one with the highest priority, followed by the phenyl group. So this is 2, and then the methyl is number 3, and then so the proton will be on the dash bond. So let's put the phenyl group and then the methyl group in the plane of the molecule. So this is the phenyl group now, and then let's put the bromine on the wedge bond. So this is bromine, and then let's put the proton on the dash bond. So this is a proton. Now let's determine the configuration. So bromine is 1, then the phenyl group is 2, methyl is 3, and then the proton is at the back of the molecule. So you see that it is going in the clockwise direction, which is an R. So this is an R molecule. So these are the drawings of these molecules in a 3-dimensional structure. So now it says that suggest a means of converting cyclohexene to the following. The first one is cyclohexene to cyclohexane. So this is cyclohexene. We are supposed to convert it to a cyclohexane. So the way to do this is to do the hydrogenation. So we just put hydrogen gas in platinum catalyst to convert the cyclohexene to cyclohexane. And the second one is trans-dibromocyclohexane. So this is a trans-dibromo. So this one is supposed to be on a wedge bond and then a dash bond. Then we are supposed to convert cyclohexene to a trans-dibromocyclohexane. So in other words, we are starting from a cyclohexene. Let me do it this way. So in this way, we are going this way. So from cyclohexene to a trans-dibromocyclohexane. So all we need to do is to put in the bromine gas, and then what it will do is that this mechanism, if you look at the mechanism of this reaction, it goes through the cyclic brominium ion, and that is what is going to cause it to form this trans-dibromocyclohexane. Then the next one is cyclohexyl alcohol. So we are supposed to convert cyclohexene, so this way, cyclohexene to a cyclohexyl alcohol. So we are supposed to convert it to something like this. What do we do now? This is just, so we are converting an alkene to an alcohol, but then because this carbon and this carbon are equal, then there's not going to be regioselectivity here. So what we need to do is to do the oxymercuration demercuration reaction. So, and that takes place in mercury in the mercuric acetate in sodium borohydride. That will give you this. So the second part of the question says that the reaction of 2,3-dimethyl butene with HBr leads to the formation of an alkyl bromide. So let's draw 2,3-dimethyl butene. So this is a butene, and this is 2,3-dimethyl butene. If we treat this with HBr, what will happen? So this is HBr. Because this is a nucleophile, it will donate lone pairs of electrons to this electrophilic center, because Br minus is more electronegative than the proton. So that will cause this bond to break, and we are going to form this carbocation in solution. So this is the proton. So there's a carbocation formation at the side. So the Br minus because it is nucleophilic, it's going to add on to the opposite carbon. So that will lead us to the formation of this molecule in solution. So this is the Br, and then this is the proton. Now, if you continue with the question says that on treatment of this alkyl bromide with potassium hydroxide in methanol, elimination of HBr occurs, and the hydrocarbon which is formed, sorry, there is an omission there, which is formed is isomeric with the starting alkene. What is the structure of this hydrocarbon? Now, if you treat a haloalkene with potassium hydroxide is a very strong base. So this proton, there's also another proton here, and this proton are readily available for the hydroxide to pick. So what will happen is that in solution, this hydroxide can pick this proton. When it picks this proton, it will cause this bromide atom to leave. And when that happens, we are going to go back to our starting material, which is this. Or another thing that could happen is the potassium, the OH minus could pick this proton. When it picks this proton, these bonds will be moved here. So when these bonds are moved here, it will cause this one to leave. When it leaves, we are going to form this kind of molecule. This is the molecule we are going to form. Instead of a 2,3-dimethyl-butene, we are going to form a 2,3-dimethyl-2-butene. Now, you see that 2,3-dimethyl-2-butene is an isomer of a 2,3-dimethyl-1-butene. Now, why is it that the reaction will favor this process more than this? That is, the reaction will favor the formation of 2,3-dimethyl-2-butene more than a 2,3-dimethyl-1-butene. The reason is because 2,3-dimethyl-2-butene is more stable than 2,3-dimethyl-1-butene, because this double bond is a tetra-substituted double bond, whereas this is a tri-substituted double bond. For the alkene, the higher the substitution around the double bond, the more stable the molecule is. Give the major organic product of the reactions below, paying particular attention to regio and stereochemical outcomes. Provide detailed mechanism for reactions B, D, and H. So if we come to A, this is a butane in the presence of hydrogen gas and then Lindlar's catalyst. So this is going to form a cis-butene because it's a Lindlar's catalyst. So this is going to form a cis-butene. And then this one is this molecule in HCl and carbon tetrachloride. Sorry, this is going to follow the Markovnikov's reaction, and therefore you are going to get this kind of molecule. So the chlorine will come to this side, and then the proton will go to the side. This is not the only molecule that will be formed in solution. Now, the other molecule that will be formed, is this molecule. Let me draw it down here. The chlorine will come here, and then this is the proton. Now, when I show the mechanism, I will show why this is also one of the possible products that are formed. So it is this product and this product that are formed in solution. Now, this is a hydrogenation reaction. So in this case, it is just going to, a double bond will just disappear. These are substituted with the protons. So this is just a hydrogenation reaction. Then this is an alkene in the presence of Br2 in carbon tetrachloride. It is going to form a vicinal dihalide, but this vicinal dihalide is a regioselective vicinal dihalide. So it's going to form a trans vicinal dihalide. because the mechanism of this reaction forms the cyclic brominium ion. So this is going to be Br, and we can put this on a wedge bond. So this is what is going to form in solution. And then is enantiomer. So it is actually enantiomers of two compounds. So this can also form in solution. So this one too is also a possible this thing that can form in solution. So this is enantiomers. Then the next one, we have this molecule in chlorine gas. So you see that this one too is also going to form a vicinal dihalide, and that is going to look like the previous example. But in this case, this carbon atom and this carbon atom are the same, and therefore it's just going to be one product that is formed, whereas this will form two products of enantiomers. This is going to form only one product. So this is a product that will be formed. So it's actually a trans product that's going to be formed. And then this is a dihalide in zinc dust and ether. What this reaction will produce is an alkene, and it is going to be an internal alkene, because where these chlorines are will vanish, and then there will be a double bond formed at that point. So this is the alkene that will be formed. And then a butane in liquid, lithium in liquid ammonia. So that's going to form a trans product. It's going to give us a trans alkene. So this is what to be formed for this conversion. Now, you see that this reaction follows the Markovnikov's addition. So what will happen is that we are starting with the alkene. Now, this is an HCl. So if you consider this reaction, this is actually an electrophilic addition reaction. Because chlorine is highly electronegative than the proton, it will pull electrons to itself. So this will assume a partial positive charge, and this will assume a partial negative charge, making the proton an electrophilic center. So this will bring this lone pairs of electrons to pick this proton, causing this chlorine to leave. So when it leaves, we are going to form a carbocation in solution. So this is the carbocation that we are going to form in solution. So this is the proton. Now, when this forms, remember that we threw out Cl minus, right? So if the Cl minus comes to donate its lone pairs of electrons into this center, then we are going to form this first molecule, which is this one. So if we do that, then that will lead us to the formation of this molecule. Or another thing that could also happen is, let me show that one here. There is a proton here. So we could have what? A proton shift. So this proton will shift to this side. So when there is a proton shift, this is resonance structure. So it's going to cause this kind of intermediate to be formed in solution. So the proton has been shifted to here. So this is the kind of carbocation that will be created in solution. So the Cl minus will then donate its lone pairs here, and that will lead us to the formation of this molecule, which is this one. Now, from the question, it says that we should determine the major product. Now, you see that between these two, this molecule will be the major product. The reason is because it is coming from a tertiary carbocation. Tertiary carbocations are more stable than this, which is a secondary carbocation. Now let's come to this one. So from this alkene, we are adding Br2. So let's start with the alkene. And then we have Br2 here, Br, bromine gas. So what will happen is that this alkene will donate its lone pairs to this bromine, but bromine has 3 lone pairs around it, so it will use one of its lone pairs to attack the adjacent carbon. And because bromine cannot form 3 bonds, it will cause this bond to break off. So when it breaks off, we are going to form the cyclic brominium ion in solution. So this is bromine. So this is what we are going to form in solution. When we form this molecule, intermediate in solution, the Br minus that we cleaved off, it cannot attack from this side. It can only attack from the opposite side. And there are 2 ways in which it could attack. It could either attack this carbon or attack this carbon from the side. So if he attacks from this side, it will cause this one to break, and that will lead us to this product. Or if, let me draw the intermediate again. Or if the bromide anion attacks from this side, and it will to cause this one to break, and that is what is going to lead us to the formation of this molecule. So this is a mechanism that leads to the formation of both molecules. And at the end of the day, because both are equally substituted, then it will be difficult to determine the major product.